Hi everyone, thank you for joining. My name is Max. This is the slide about me. What is important to today's talk is that I'm an infrastructure engineer at Manychat, and one of my job responsibilities is to optimize performance of Manychat application. I'm a bit nervous to give the speech in English, but I want to talk about something that is very interesting for me, and I hope that it will be also interesting for you. I will try to keep it simple, and I hope I will succeed in this. So the agenda of my talk will be the context of the problem, what we do in Manychat, and the challenges we face with high concurrency HTTP requests, the solutions that we have found, some numbers about them, and code examples. Afterwards, I will be able to answer your questions. So as Anton mentioned, Manychat is a leading chat marketing platform. We help businesses to establish meaningful conversations with their customers using WhatsApp, Instagram, Facebook Messenger, Telegram, and recently TikTok. Here, how this looks. Our customers can create interactive flows to communicate with their subscribers. In this example, subscriber can scan QR code or click advertisement link or just a link in internet or just send a simple message elephant to the business. As an action that is triggered by this starting point, we instruct the AI agent that we want the AI agent to find out the preferred color for the customer. It should be either blue or pink, and depending of what the AI agent find out from the customer, send him either blue or pink elephant. So pretty simple flow, but Manychat is much more than that. There are lots of other options. You can even make your own integration using this visual flow, making HTTP requests to your own system. But I would like to focus on this case as a simple one. So you can imagine that we make a lot of HTTP requests, and the problem with HTTP requests in PHP, is that PHP is, as you know, is synchronous. It's only one single thread, and it performs every step one by one. First of all, you need to prepare the request, the URL, body, method, headers. Then you need to establish the connection, make SSL handshake, transfer all the requests over internet, wait for the server to give you the response, download all the response, and then only handle this response. That's one of the key why people don't use PHP to do all this work. Most of the time they use, for example, Nginx as a web server in front of PHP FPM to offload much of the burden from PHP of establishing concurrent TCP and SSL connections with the client to buffer the incoming request body, and only then transfer it to PHP, and buffer the response from PHP, and then transfer it back to the client. And Manychat, when we exponentially grew, had a problem with this approach, and Nginx plus FPM wasn't enough for us because you can imagine if there are lots of concurrent requests, you need to have the same amount of PHP workers to handle all those concurrent requests. So we came up with our solution with several iterations. We have decided to offload even more to Nginx using Lua, the embedded language in Nginx. We process the webhooks, determine their type inside Lua, and store it to Redis queue webhooks of different webhook types, and then process those webhooks in command line PHP workers. And by using this approach, first of all, we save up on PHP initialization. Contrary to what PHP FPM does, in command line worker, we can initialize the framework, the afterload, and all this stuff at the start moment of the worker when it serves the first request. After that, you have all your classes autoloaded, precompiled, already in memory, and then you just again process the next request and the next one and the next one. So this saves a lot of time. And in addition to that, using this technique, you can smooth the spikes of the requests. So when there are too many concurrent requests, you just can store them in the queue and don't serve them until you have more workers to serve. Yeah, so that was the solution for the first part of problem. But we still need to make the request to the LLM model to AI. And to do that, we need to make all this stuff inside PHP, the establishing the connection, transferring the requests, and most importantly, wait for the response. As you probably know, the AI models may take from seconds to minutes to provide the response, depending on the prompt size. And if there are lots of concurrent requests that are making the request to the AI model, you will end up with all the workers, all of them waiting for the response and effectively doing nothing except consuming the memory and maybe more importantly, database connections, cache connections, logger connections, and all these resources that you need to keep it running. So we decided to take similar approach to offload this burden from PHP somewhere else. To do that, we decided that in our flow, before making the request to sorry. Yeah, I'm pointing the wrong direction. Oh, magic. Oh, do we have cats here? Yay. Yeah, instead of making the request on PHP side, we just prepare the request there, serialize the request itself, the business process state, like what is the user, the customer who are communicating with us, and all this necessary stuff, and just send the task to some more specialized worker that is more capable of doing concurrency, concurrent requests in parallel, so that this worker will take the requests from multiple of those synchronous workers, take all the requests and serve them, serialize the response to those requests, and take the state that we previously sent to it and return it back to the pool of workers to deserialize the response and process the AI model response. Before going further, I'd like to ask you, what are your ideas? What are the best, or maybe your preferred language to make those concurrent, quick, parallel, lots of parallel requests? Maybe, why not? I've heard the options, not Java, but superset of Java, Kotlin. Kotlin. Another option, Zeek, Rust, Go with coroutines. So there are plenty of solutions for that. And we decided, okay, let's try Go. Why not? It has those coroutines. It's a bit hypey, fast, but it's always a problem to introduce a new technology, because it's a different ecosystem. You need to deploy somehow the code that will work with your code and integrate it. So before doing that, we decided to do the proof of concept of this serialization and deserialization of business logic, and just use PHP Guzzle library that we already use as this pseudo parallel concurrent worker, just to make sure that we can serialize, deserialize, make request, serialize again, deserialize, and everything will work from this point of view, and only after that introduce Go. And so we thought that Guzzle will serve those requests sequentially, but Guzzle has the async interface similar to sync interface, so at least we will get this one. It still runs in single thread, but luckily, instead of waiting for the response, in that spare time, we still can serve another request, establish the connection, the SSL handshake, etc. Additionally, spoilers alert. Additionally, this allowed us to reuse existing connections. As you can imagine, the request to the same ChatGPT model is done for the same URL, so we can reuse existing connection. Plus, as this is the HTTP2 connection, we can use HTTP2 multiplexing by making multiple requests using one TCP connection. Yeah, and spoiler, the proof of concept went so well for us that we have found out that this serialization and deserialization took like a sub-millisecond to do. So they lose on this switch between different type of workers compared to seconds or minutes of waiting time from the LLM model is nothing. And turns out that for tens of thousands of active synchronous workers, we need only 300 asynchronous workers. And actually this number is limited by minimum number of workers that we run per server. Actually, most of the time they don't do anything. They just serve those requests, and dozens of thousands. Those 300 workers does dozens of thousands of asynchronous external requests per minute, and for hundreds of thousands incoming requests per minute, we have to make hundreds thousands still synchronous requests, sending the response to the customer with the elephant. So the point of an improvement for us was not to introduce Go to do that, but to change our business logic of sending the HTTP request to Meta, for example, to send the response to the subscriber. And that's what we will do next. Before, yeah. Now I'd like to show you the code examples. I have. Oh, this will work better. It zooms. So the biggest challenge that we anticipated is to serialize our business logic. And what are the caveats of business logic serialization? If you just use native PHP function serialize and serialize PHP objects, you can end up in the situation when you serialize an object inside an object inside an object, and it will held inside some resource that is not serializable. Or there can be some database data that will be stale in a few seconds or something like this. So we decided that for business logic part, we will just implement completely custom serializer extending basic PHP JSON serializable interface. So the serializer and the serializer with wake up procedures that will go to database, take the actual data, or not database, but the intermediate cache that is kept up to date, just to be sure that everything from the business perspective works smooth. Additionally, why we decided to use this JSON serializable approach is that if you serialize natively with PHP, it serializes the object itself. And if the developers do some refactoring, change the class description, or maybe moving it from one folder to another and changing it namespace, it can turn out on deployment that you serialized the one version of code, but deserializing the other version code, you will end up in incomplete class and business logic failure. So we decided to keep wrong button, sorry. To keep this safe approach, to make sure that developers do this all by hands and they know what they do. But for the jobs that we sent to between those workers, we decided not to be so strict, but still to use only primitives in our data that we sent, because in addition to, for example, and primitives that won't have resources, obviously, and use public properties only, because PHP native serializer for private properties, for every property, write the whole namespace of a class in serialized string, so the serialized object becomes too big it doesn't make sense to serialize so many data. And we decided that we are okay with the fact that we cannot refactor much those jobs because there is nothing to change here a lot. And if we will have, we will just introduce the new object and switch to it if we will need this. Okay, next one. Another interesting for me thing was how to serialize the request and the response. Turns out that requests and response are just HTTP standardized strings. And Guzzle library has the basic method toString to serialize the response. As you can see, it's just a HTTP version protocol version, the host headers, other headers, and the body inside. Another thing that I wanted to highlight here, this is string check before a start over for the name of the header. That's our contribution to Guzzle library. Turns out one of our clients decided to send strange header to his server, but completely compliant with HTTP protocol. He just sends number there as a header name. Yeah, and the library failed on this str to lower on integer. Yeah, now this fixed and it works pretty well. Another thing that we had to work on serialization was the exceptions that are thrown by Guzzle. Unfortunately, there were no native Guzzle serializer for exceptions, so we had to make the custom one, but there are not too many exceptions, so this is the whole serializer. As for the exceptions request and response interface, we just use this native message toString that I have showed you earlier. And this is the exception deserializer. For message, it uses the native parse response that takes this HTTP standardized string and creates Guzzle's request object back from this. Yeah, another interesting part is how the worker works. So it basically takes the payload from the request, takes the request from the payload and sends it to native Guzzle client function, send async, and providing two closures: what to do in case on success and what to do in case of failure. And here we have the catch function that does the same function call as in case of rejection of the failure. This function returns almost immediately because it don't make the requests right now. It just adds the requests and those two closures to its Guzzle's internal queue. So we can do this process job as many times as we want. We just made the assumption that 400 requests in flight is enough for one worker. So we increment the number of those tasks in flight, and if there are more than 400, we just stop pushing this worker. The magic happens on after iterate after this function. We call the Guzzle's native function tick. This function basically makes the requests if there are new requests in queue, then checks all its handlers if there are any responses and gets the responses. If they get the whole body of the response, it calls the closures that we provided earlier, either success or fail. Here how it looks under the hood in the Guzzle. Yeah, it adds to the queue and calls underline libcurl multi-select function and multi-exec function that do all this magic that I have described in a non-blocking fashion. So if there are nothing to do right now, no new requests to make, or no responses that are ready to be received from the socket, this function just returns the execution back from the library to PHP. And if there are something to do, it does it, and if the response has been completed in full, calls this process messages that will call our closures that we made send it. So let's have a look at those closures. Those closures create the job for the synchronous worker. For success case, it serializes the string with the method that I showed you earlier and passes the context back as is. And for failure case, it serializes the exception and passes the same resume job to the synchronous worker. So let's sum up. We decided to prepare a request in one worker, serialize it together with business data, and pass it to other worker. With multi-exec function, they are simulatedly parallel, and there was no need for grown-up highly concurrent solutions like pthreads or parallel for PHP or additional language like Go or something else. And we saved here on this waiting time, on reusing the established connections and utilizing the HTTP to multiplexing. And what is important here is to be careful with serialization. Serialize either the primitives or write the custom serialization for the objects. So thank you. It was a great pleasure to give you this talk. We have few minutes left. I can answer the questions if you have.
Yep. Thank you, Max.